The composition of a protein is defined as the amino acids within the protein and their relative amounts. How would you go about determining the composition of a protein? Let's again examine a hypothetical polypeptide. If we could subject the polypeptide to a reaction that cleaved the peptide bonds but left the amino acid side chains alone, determining composition would just be a matter of analyzing and quantifying the products of such a reaction. Let's assume for now that such a reaction exists. What would we then have to do to the soup of amino acids that results? Each may have to be tagged with a molecule that's visible to some analytical method. We'll see that fluorescence spectroscopy has been used for this purpose in the past. After tagging, we would just need to separate the various amino acids and examine them using the analytical method of choice. Thus, we see that reaction, tagging, and separation are the three steps involved in determining peptide composition. In practice, the peptide cleaving reaction used in the laboratory is acidic hydrolysis. Under acidic conditions, protonation of the amide, followed by nucleophilic addition by water, produces a carboxylic acid and amine from the starting amide. This process liberates free amino acids, but detecting the amino acids is difficult without an additional tagging step. The tagging molecule is orthothaldialdehyde, or OPA. This compound is used because it forms a highly fluorescent isoindole ring in the presence of an amino group and beta-mercaptoethanol. The fluorescence of these compounds is a consequence of the small HOMO-LUMO gap of the isoindole aromatic ring. The fluorescence intensity of the isoindoles tells us how much of each amino acid is present in the protein. To separate the soup of isoindoles, we use chromatographic separation. We place the mixture on a negatively charged column of material, and as you might expect, the negatively charged amino acids move rapidly through our negatively charged column, while the positively charged amino acids are attracted to it and stick to it. By measuring fluorescence intensity as isoindoles elute from the column, from most negatively charged to most positively charged side chains, we can determine the relative amounts of amino acids in the sequence. All in all, as long as we can identify the peaks within it, a chromatograph like this tells us everything we need to know about the overall composition of the protein, including the identity and amounts of all the amino acids within it. Let's take a moment to examine the mechanism of isoindole formation from OPA and an amino acid, the tagging reaction. OPA's two aldehydes make it highly electrophilic, and nucleophilic attack by the amino group on an aldehyde carbonyl carbon is the first step of the mechanism. After proton transfer and beta elimination of hydroxide, we arrive at the first intermediate drawn on this slide, the iminium ion. The positively charged iminium ion is, as you should expect, even more electrophilic than the aldehyde, and it's easily attacked by beta-mercaptoethanol in the next step. After another proton transfer, beta elimination produces yet another iminium ion. This ion is highly acidic and may be deprotonated by nascent hydroxide, leading to the neutral isoindole product and two equivalents of water. Using the highly fluorescent ring system of the isoindole, we can then see each amino acid by fluorescence spectroscopy. A more ancient method of tagging, which requires the soup of amino acids to be separated first, involves the formation of purple dye from the molecule ninhydrin. Give this mechanism a try on your own. Also, recognize that the purple color that results when we subject an amino acid to ninhydrin suggests the analytical method of UV visible spectroscopy to determine the amounts of each amino acid in the sequence.